For this webinar, a talk will be given by industry professional invitee, Dr. Miguel Bernal from Barisonics, followed by our academic speaker, Professor Ivan Rosado Mendez from the University of Wisconsin. And moderating our session today is Professor Roberto Lavarello from Pontificia Universidad Católica de Peru. During the webinar, please type your questions in the chat box at any time. They will be answered during the Q&A session of this webinar. If you would like to ask a question during the Q&A session, please raise your hand to switch on your camera and unmute to ask your question. Automatic closed captioning is available that you could see at the bottom of your screen. Please press the closed captioning button or CC button and choose show caption to enable it at any time during the webinar. I'd like to introduce you now to our organizing committee. We have Hermes Kamimura, the Latin America Outreach Initiative Chair. We have Sophie Morse from the Volunteer Engagement Committee. We have Andrea Polito from the Latin America Outreach Initiative as a volunteer. We have Patricia Cardoso de Armande from the Latin America Outreach Initiative as well, and Stephen Lee for the Latin America Outreach Initiative for video editing. Patricia and Andrea will translate typed questions that are asked in Portuguese and Spanish to English for the moderator. And I will give it to Hermes Kamimura for announcements.
Hello, everyone. My name is Hermes Kamimura. Welcome to our second America Latina in Foco webinar. Our outreach initiative is growing fast, and we are very happy to see the increase in the participation of Latin Americans in our events. If you have speakers to suggest, please reach out to us and sign up for our mailing list for more information. And Andrea will put some links for you during my announcements. Can you put the announcements, please, Lacey? As this pandemic situation is dynamic and the affected areas continue to shift in Latin America, we have to put an extra effort to network and share our research. And these virtual events, such as this webinar, allow us to somehow compensate for the lack of these in-person opportunities to meet. We also use this webinar to bring you some announcements that include with volunteer opportunities and other virtual events as important resources to us, and most of all to our students to experience scientific events and meet research colleagues from all around the globe. In the next slide, I want to start with a volunteer opportunity. So the UFFC Society has an open position for a Latin American representative in the diversity and inclusion team. Please contact ALP, our D&I chair, or the volunteer engagement committee using the link that Andrea will put in the chat. You can also chat during this webinar with me and Sophie. We can also provide you more information. In the next slide, ALP also is organizing a workshop with the electronics division of the American Ceramic Society. And the workshop is called World Outreach Workshop on Materials Technology and 5G Communications. And it's being held virtually on July 7. The registration is free and Latin Americans are strongly encouraged to join. Please check the website in the link you can see in the chat box as well. The next, please. We are very happy to announce that the abstract submissions is now open for the Latin America Ultrasonic Symposium. Our deadline is July 2nd, Friday, so please go ahead and write your abstract. And please join us in this unique opportunity to network and increase the impact of Latin Americans in the IEEE Society. We hope that this virtual experience allows us to learn and create a sustainable series of events to integrate more and more Latin Americans within the IEEE community. Your participation is essential to us to continue these efforts, and the link is also there. Many links for you today. The next one, another important event is from October 12 to 22. We'll have the Summer School Transducer Waves, where students primarily from Canada and Latin America will learn the main pillars of acoustical imaging. Please reach out to Koen van Doggen for more information. And the next one, we have, for the students present here, we have a PhD position available. This opportunity is with Professor Paco Camarena in Valencia, Spain. We also highly encourage the participation of Latin Americans in this program. The Professor Paco Camarena email will be also in the chat box. Finally, the next slide, we have Madeline, a student representative for UFFC Society here today, and she will be explaining us how to get involved in student activities. Thank you so much, Madeline, for joining us. The floor is yours.
Thank you, for the nice introduction. So my name is Madeline, and as you already told, I'm a student representative for ultrasonics within the UFFC Society. This is probably the most visible position you can have within the society as a student, because you will organize student-geared events during the conferences, which is super fun, getting to know all the students and look behind conferences, how they are organized and what you can do there. And also to connect with a lot of leaders worldwide, because they are helping us to organize all those conferences. So if you're interested in joining us, just reach out to us. We are on the website. You can email us. The information should be up on the UFFC website. But that is not all. You don't need to be a student representative to join the society. You can also be a committee member, as Hermes already mentioned, for example, in the Diversity Inclusion Committee. And there are a whole lot other committees you can join. You can also find them on the website in the volunteer section, and you can see whether you're interested in joining here and you want to do your part and be active within the society. We are also trying to set up a student engagement initiative where we want to do more for our students and have student-geared workshops and even more networking opportunities for us to just get connected within our topics and society. That's it, what I have to say. I give it back to Hermes. Thank you very much.
Yes, so we'll continue now with Sophie. Please, Sophie.
Yeah, so it's with great pleasure that I'd like to introduce you to Miguel Bernal, who's actually a senior ultrasound scientist at Verisonics and a subsidiary of the company for South America. He actually did his degree in biomedical engineering at the School of Engineering of Antioquia in Colombia. And then he did his PhD in the Mayo Clinic in the US. And he moved to Paris after that to do a postdoc with Miguel Tanter, and then returned to Colombia with a fellowship at the Universidad Pontificia Bolivariana. And he's been working now for Verisonics for 3 years. And with that, I'll let you enjoy hearing about the high frame rate volume imaging work that he's now going to show us. Thank you.
Sophie, thank you very much for that introduction. Let me share my screen, and please let me know when you see my slides.
Yes, we can.
Good. So today I'm going to talk about high frame rate volume imaging through a technique that we developed that is called sparse random aperture compounding. So let's first, why do we care about volume imaging? So as most of you know, there's a lot of complex body structures, and getting them in a single plane, it's usually very complicated. So you need to be very well trained at imaging with ultrasound in some of the cases, and then this comes at operator dependency. So you need to know what you're doing, and more on that is that there are certain applications with out of plane motion becomes critical. For example, in this case, we're seeing the blood flow in the left ventricle, and as you can imagine, there is a lot of particles that are moving in and out of the plane. So if you want to be able to characterize this properly, then you need to do volume imaging. And why do we care that is high frame rate? And when I mention high frame rate, I'm talking about thousands of volumes per second. And the idea is to be able to characterize complex phenomena that happen fast within the body, for example, blood flow. But there's also certain applications that have been developed in the last 20 years that make use of high frame rate, for example, shear wave propagation or functional imaging or tracking of single bubbles for super resolution. So that's the motivation behind this technique that we developed. When you think of high frame rate volume imaging, you start with a probe that usually has a lot of elements. In this case, we're going to be talking about 1,024 elements. And you have two options. You either have a system that has as many channels as elements in the probe, which is what I'm showing, in that 1024 channel system, or you have a system that has less channels than elements in the probe. And then, as you can imagine, the difference between these two systems primarily is the price. In one case, it will be a very expensive system. The other one will be a lot more, will be cheaper. So the idea and what we decided to do was to create, a technique that allow you to do random, you select certain random elements within the probe and you try to image with them. And then what you do is you actually image with a different set of random elements, and then you compound the images. So the idea was to explore the quality of the images and how to use these apertures, which can be complementary or non-complementary random apertures. So when I mention complementary random apertures, this is what I mean. So we have 256 channels in the system, but we have 1,024 elements in the probe. So we're going to choose certain elements at random, and then we do an image with that with those elements. And then we choose a second random aperture that is complementary to the first one, meaning that there is no elements that are going to be repeated. Then we choose a third one and a fourth one. And then by doing this, what we do is we recover or we use all the elements within the probe to do imaging. Then what we initially did, the work that we initially actually published last year, we used a 3 megahertz Vermont probe that has 1,024 elements. And then we developed a series of acquisition sequences using either single plane waves, divergent waves, angle compounding, and white beams. And then we tested this on a phantom that looked like the image on the left, which is a single string. And then we did acquisitions using 1 aperture, 2, 3, and 4 apertures, where we did the compounding. We also compare it to the multi-system. And what we did is we evaluated the image quality. And for this, we did the main lobe to side lobe ratio comparisons. In this case, in the image, sort of in the middle, you can see the YZ plane, where we can see the string. And then within that red box, what we did was we averaged in the depth in order to capture all the side lobes that we were getting from this structure. Then in the next image to the right, you can see the C-scan of the average depth, and the string is very noticeable there. And what we did was we did some profiles of that string, which is what you can see on the image on the right. And I apologize because I'm trying to get okay, here is the cursor. So here, we get the profiles and we plot the profiles in this case. And what we're comparing is, this noise level to the main lobe, which is generated by the string. So this is what we call the main lobe to side lobe ratio. So the bigger or the lower the number, because these are negative numbers, the better the image quality. So when we did this, we set the string in the center of the probe, but we also set it, off the axis of the probe, just for comparison. And as I mentioned before, we evaluated different acquisition sequences. We had a single divergent wave, we had a cross angle compounding, we had a spiral angle compounding, and then we have the white beams. And what we saw is that, when we use 1 random aperture, in this case, we get a value around, minus 12 dBs. And as we start compounding, adding apertures, we increase the main lobe to side lobe ratio. And if we compare with the multi-system, which is in black, you can see that there's still, some advantage of using the multi-system. However, by using 4 random apertures, you're almost there. The cross and the spiral, since they have angle compounding, they showed, better image quality. And the white beams, which is a script developed for high quality imaging, outperforms all the other ones. We saw the same behavior for the off-axis string. And this initial results demonstrated that sparse random aperture compounding was actually a technique that you could use for volume imaging at high frame rates. This is just one example of an aneurysm phantom that we use to image. In this case, we're using the white beams, and in this case, it's only one random aperture. And here you can see the volumetric reconstruction of the pulsation of the aneurysm phantom. And here you can see the XZ and the YZ planes. So this demonstrated that, you know, we could actually do some imaging and do some volume reconstruction in these cases. Then, you know, what we were interested, so what I showed you before is what we published last year in physics for medicine and biology. And then after that, we started posing certain questions. And you know, in that publication, we used random apertures. And in this case, we generated random apertures using the MATLAB generator. But are there some random apertures that are better than others? What happens, you know, if the apertures are actually not complementary? What happens if, you know, you use a different sorting mechanism for what's better? So what we did was we created 1,250 groups of complementary random apertures that I like to call families, which means that we have 5,000 apertures in total. And then we use the same phantom, a string phantom, and we did some preliminary acquisitions using those 5,000 apertures, and we reconstructed just a small volume or a small section to be able to get a sense for the image quality that those apertures would generate. So here in this graph, you can see there's, you know, the aperture number from 0 to 5,000, which is all the apertures that we tested. And here's the main lobe to side lobe ratio. You can see that there are some apertures that are a lot better than others. So we have, for example, here, one aperture that is at -16.5, while we have another one around here that is, you know, that's around 7. So there is a big difference, you know, in the main lobe to side lobe ratio, depending on the aperture that you choose. So what we did was we sorted these apertures based on the main lobe to side lobe ratio. And you can see in this case would be the best ones. Here would be the worst ones. And if we zoom on the best ones, we can see the first 10. We can see that this one will be the best aperture that we found. This will be the second one, which would be the best. But if you think about it, this first one is actually the aperture 1,263 that has the main lobe to side lobe ratio of -16.56. But its family is not the aperture immediately next to it, but are the, you know, 1,261, 62, and 64. So what we did was when we did this sorting, we chose this one and we chose the family members. And that's what we called the U sort. The other thing that we did was we sorted by the family average main lobe to side lobe ratio. So we took the average, you know, the value from all these 4 apertures. We got an average value, and then we did a similar sorting to this, but based on the family average. And then that's what we call the M sorting. So we created the U sort where we have the best one, the best individual and its family. And then we have the M sort best, which is the best family. And then what we did was we evaluated the image quality using the main lobe to side lobe ratio, as it was described in the previous slides. We used a single diverging wave in this case, and we did the acquisition of the phantom, and then we reconstructed the entire volume. In this slide here, you can see, you know, what happens when you use the best individual or the best aperture of those 5,000 apertures. You can see that there is, you know, you can see the string here, and you can see that the noise level is, you know, is fairly low. In this case, is around, you know, -16 dBs. While when you look at the worst aperture, you can see that the noise level it's a lot more present. It's a lot higher. In this case, around, you know, 6 or 7 dBs. So when we look at the main lobe to side lobe ratio, you know, there's a clear distinction if we look at the profile in this case compared to this case. We can see the blue one is for the best one, the black one is for the worst one. If we calculate the main lobe to side lobe ratio, we can see that there is a clear difference in the 2 apertures. In this case, that difference is about 9.5 dBs. So what happens if we start doing compounding with these apertures? So in this case, we're doing compounding of the best individual and its family. Well, here we're doing compounding of the best family. So these are, you know, one aperture, which is the best one. This is the family members of this one individual. And here is just the best family with the best individual being used first. And we can see that there is a difference whether you use the best individual and its family, or the best family for image quality. And then the results shown here in green are from that paper that we published last year. So remember that those apertures were just random apertures chosen in, quotations randomly. So there's a difference whether you optimize the apertures or not. Then here is, the same results in, blue, red, and green. And then what I added here was, the results in black, which is, the worst individual and its family, and the worst family. Then we can see that there is a huge difference, or a very significant difference between, if you choose a good individual and its family, or a bad individual and its family. And the same is true for, the families of the apertures. It's a lot better to use a good family than a bad family. And even if you compare it with those random apertures chosen for the initial study, that is true. Then the next thing, the next question was, what happens if you use complementary random apertures versus non-complementary random apertures? So we saw that the complementary random apertures are those sets of apertures where elements don't repeat. So what happens if you just take apertures at random and you optimize those? So here, these are the same results that I showed you before for the best individual and their families, the best family. And then what I did here was I actually used the best apertures, from those 5,000 apertures that were optimized, or that were evaluated. And I actually compounded the best one with the second best one with the third and the fourth. And what happened, and it's clear here, is that, this one is the same as this one because it's the same individual. But once you start compounding, complementary, you actually outperform, the second best aperture. So what this means is that, complementary apertures that make a difference, and, they're a lot better for image quality. So this, I'd like to conclude my talk. So, compounding of sparse apertures provide a good alternative when the number of channels in your ultrasound system is limited. Sparse random aperture compounding is suitable for high frame volume imaging using matrix probes. Sparse random aperture compounding provides a balance or a trade-off. It allows the user to determine the trade-off between, the image quality and the frame rate, because as we mentioned before, the more apertures you compound, the lower the frame rate, because you have to do more transmits and receives. We saw there is, there could be up to a 9 dB difference in our case, in this study, for when you optimize the apertures. And then, it's better to compound, using the best individual and its family than it is to compound the best families. So the individual, it actually plays a big role. Lastly, complementary random apertures provide better performance than non-complementary random apertures. And then some of the future work that we'd like to do, it's, what happens when you start doing aperture compounding or optimization of aperture compounding, and then you start adding the angle compounding at the same time. Because as I mentioned in the introduction, we created those scripts that actually do angle compounding as well. So we wanna see if it is true when you optimize for a single diverging wave, if that translates to angle compounding as well. And then there is, the question of, is compounding a commutative property? So is it the same if you do the best aperture and you compound it with the worst, or if you do the worst with the best? And then lastly, the idea is to evaluate different optimized apertures at different depths, and then some imaging of some, tissue phantoms, because in this case, it was a very primitive and simple phantom. And with this, I'd like to thank you all for your attention, and we'll take some questions after, the second talk.
Thank you so much, Miguel, for showing us these really interesting results. Thank you. So please post any questions at any time in the chat for both Miguel or Ivan's talk, which you're about to see. And if you'd prefer to type them in Spanish or Portuguese, then please do. But before we go into the Q&A, I'm going to introduce Professor Ivan Rosado Mendez, who's going to be talking to us about quantitative ultrasound using in obstetrics and neonatology. He has a degree in engineering physics from the Tecnologio de Monterrey, and then he did his master's in medical physics from the National Autonomous University of Mexico. And after that, he did his PhD and postdoc at the University of Wisconsin-Madison. And in 2017, he actually became an assistant professor at the Institute of Physics of the National Autonomous University in Mexico. And only recently, he's returned to Wisconsin-Madison as an assistant professor in the Quantitative Ultrasound laboratory. So with that, I'll let you enjoy his talk, where he's going to be telling us about 2 applications actually of quantitative ultrasound to provide non-invasive biomarkers of tissue structure and function. So enjoy, and please type in any questions in the chat at any moment.
América Latina en Foco.
Hola, buenas tardes. Es un gusto saludarles desde la Universidad de Wisconsin en Madison. Agradezco a las y los organizadores de esta serie de seminarios en foco para América Latina, en especial a Hermes Kamimura, por la invitación para compartir con ustedes el día de hoy parte de mi investigación enfocada en la aplicación del ultrasonido cuantitativo en obstetricia y neonatología. Los resultados que les presentaré hoy surgen de una colaboración entre la Universidad de Wisconsin-Madison, la Universidad Nacional Autónoma de México, Intermountain Healthcare y la Universidad de Duke. Quisiera también agradecer a mis colegas, los doctores Timothy Hall, Helen Feltovich y Chris Economidu, quienes me han permitido colaborar en sus proyectos para comenzar a desarrollar mis propias líneas de investigación. Estos proyectos han estado financiados por los Institutos de Salud de los Estados Unidos, así como por la Universidad Nacional Autónoma de México. Agradezco también a Siemens Healthineers por el apoyo técnico y el préstamo de equipo, así como al Centro de Investigación en Primates de la Universidad de Wisconsin. Comencemos. La plática estará dividida en 4 partes. Comenzaré dando una introducción breve a lo que es el ultrasonido cuantitativo y posteriormente les presentaré algunos resultados de la aplicación de estas técnicas en obstetricia y neonatología, para cerrar con mensajes finales. El ultrasonido cuantitativo enmarca un conjunto de técnicas de procesamiento de señales e imágenes adquiridas con equipos de ultrasonido para extraer descriptores cuantitativos de las propiedades estructurales y fisiológicas de un tejido. Por ejemplo, esta figura muestra un conjunto de imágenes que proveen información cuantitativa de un carcinoma ductal infiltrante mamario a través de diferentes mecanismos de contraste, como la ecogenicidad, la elasticidad, la presencia de flujo sanguíneo y la atenuación acústica de la lesión. Esta información se presenta en forma de imágenes paramétricas que muestran la variación espacial del descriptor de interés. La figura anterior nos muestra que existen varias técnicas de ultrasonido cuantitativo. Y en esta plática me centraré en la elastografía por onda cortante y el ultrasonido cuantitativo por pulso eco. La elastografía por onda cortante se basa en la inducción de ondas transversales, cortantes o de cizalla dentro del tejido mediante la transmisión de un pulso de ultrasonido intenso y al menos 100 veces más extenso que los pulsos utilizados para crear imágenes convencionales. La interacción de dicho pulso con un medio atenuante, como lo es el tejido biológico, resulta en la transmisión de una fuerza de radiación acústica, o ARFI por sus siglas en inglés. Esta fuerza crea un desplazamiento en la dirección de la propagación del pulso. Y este desplazamiento, que es del orden de micras, se puede cuantificar calculando la correlación de las señales de eco adquiridas antes y después de la aplicación del estímulo ARFI. Debido a las interacciones moleculares dentro del tejido, estos desplazamientos se propagarán perpendicularmente creando una onda transversal. Ahora, si creamos una gráfica de los desplazamientos en escala de colores como función de la distancia al centro de la fuerza ARFI y del tiempo, podemos seguir la trayectoria del máximo desplazamiento, lo cual nos permite cuantificar la rapidez de propagación de la onda transversal. Esta rapidez está relacionada directamente con el módulo de elasticidad o el módulo de corte, lo cual sugiere que la rapidez de propagación será mayor en materiales más rígidos o más duros. Un punto importante a notar sobre esta relación, la cual es comúnmente utilizada para derivar los valores del módulo de elasticidad a partir de la rapidez de la onda cortante, es que se basa en la suposición de que el medio es isotrópico, homogéneo y puramente elástico. Pasemos ahora a la segunda técnica de ultrasonido cuantitativo que les presentaré hoy, el ultrasonido cuantitativo por pulso eco. Esta técnica se basa en analizar las señales crudas, es decir, sin procesar, del tipo de radiofrecuencia o RF o IQ, producidas por los equipos de ultrasonido clínicos. Esta gráfica nos muestra un ejemplo de una señal RF en amarillo, comparada con su envolvente en azul, la cual se utiliza para generar las imágenes convencionales en modo B. Muchos de los métodos comprendidos dentro de estas técnicas utilizan el espectro de potencias de las señales de radiofrecuencia, es decir, la distribución de potencia de las señales de eco como función de la frecuencia. A partir del espectro se pueden calcular propiedades acústicas del tejido que varían con la frecuencia, como los coeficientes de atenuación y de retrodispersión. El coeficiente de atenuación describe la tasa de pérdida de amplitud del pulso de ultrasonido por unidad de distancia atravesada y generalmente aumenta de manera lineal con la frecuencia. Por su parte, el coeficiente de retrodispersión está definido como la sección eficaz diferencial de retrodispersión por unidad de volumen y cuantifica la ecogenicidad del medio. En particular, el coeficiente de retrodispersión es muy interesante, ya que podemos ajustarle modelos teóricos de retrodispersión acústica para extraer propiedades del medio a una escala menor que el límite de resolución espacial en modo B. Estas propiedades, como el tamaño efectivo, concentración o empaquetamiento de variaciones microscópicas de impedancia acústica, conocidas como dispersores, están relacionadas con características microestructurales del tejido, como la presencia de vesículas de grasa en el hígado, la celularidad de un tumor mamario y el contenido y forma del colágeno de la matriz extracelular, como por ejemplo en el cervix uterino. Una vez definidas las técnicas de ultrasonido cuantitativo que abordaré hoy, quisiera platicarles sobre la primera aplicación en obstetricia, que es en el contexto de parto prematuro. El parto prematuro es un problema grave que afecta a 1 de cada 10 bebés en los Estados Unidos y es la causa principal de muerte en niños menores a 5 años de edad. Uno de los retos importantes en este contexto es que las estrategias actuales para evaluar el riesgo de un parto prematuro espontáneo, como la medición de la longitud del cuello de útero y detección de un cervix corto a través de ultrasonido vaginal, tienen especificidad limitada. Por ejemplo, se estima que solo alrededor del 20% de las mujeres que presentan un cervix corto durante el segundo trimestre de embarazo en ultrasonido transvaginal darán a luz antes de las 37 semanas de gestación. Varios grupos de investigación, incluyendo el nuestro, han explorado el uso de la elastografía por onda cortante para detectar cambios anormales en la rigidez del cervix que puedan indicar el riesgo de un parto prematuro. El cervix se encuentra en la parte inferior del útero y pasa por un proceso de transformación dramática que lo llevan de ser una estructura relativamente rígida, como el cartílago de la nariz al comienzo del embarazo, a una estructura suave como la mejilla, que se dilatará para permitir el parto vaginal. Durante un parto prematuro espontáneo, estos cambios ocurren antes de tiempo. Durante mi postdoctorado en el laboratorio de ultrasonido cuantitativo en la Universidad de Wisconsin, probamos el uso de la rapidez de la onda de corte como un indicador de la rigidez del cervix en macacos rhesus embarazadas. Esta gráfica, cortesía del Dr. Timothy Hall, muestra los resultados de este estudio en macacos, en color negro, y su comparación con un estudio similar en humanos, en color azul. La gráfica muestra cajas que agrupan mediciones de la rapidez de la onda cortante en varios sujetos, como función del tiempo de gestación. En ambos estudios encontramos una reducción significativa de la rapidez de la onda cortante en el cervix como función del progreso del embarazo. Curiosamente, cuando tomamos en cuenta la diferencia en la duración del embarazo en humanos y en macacos, la tasa de reducción de la rapidez de la onda cortante durante el embarazo es similar entre las dos especies, apoyando el uso de este modelo animal. En resumen, para esta aplicación, los resultados mostraron que la rapidez de la onda cortante disminuye significativamente durante el embarazo en el cervix del macaco rhesus. Además, observamos que la tasa de cambio es similar a la observada en humanos cuando tomamos en cuenta la diferencia en duración del embarazo. Entonces, si regresamos a la relación entre la rapidez de la onda cortante y el módulo de elasticidad, ¿estos resultados sugieren que el cervix se ablanda? Bueno, la relación no es tan directa. Esto se debe a que las suposiciones de que el medio es isotrópico, homogéneo y puramente elástico no son del todo válidas en el cervix. Por ejemplo, la figura que tenemos aquí muestra imágenes de la distribución de colágeno en la matriz extracelular del cervix en una vista axial, obtenidas a través de microscopía óptica por generación de segundo armónico. Podemos notar que el colágeno está organizado en bandas o en capas, lo cual puede afectar la manera en que se propaga la onda cortante en el cervix. Actualmente estamos investigando los efectos de la estructura compleja del cervix en la cuantificación de la rapidez de la onda cortante y su interpretación en términos de cambios en las propiedades mecánicas del cervix durante el embarazo. Pasemos ahora a la aplicación del ultrasonido cuantitativo por pulso eco en neonatología. Esta aplicación está motivada por el hecho de que en el 2016 la Administración de Alimentos y Medicamentos de los Estados Unidos lanzó una advertencia contra el uso prolongado y repetido de ciertos anestésicos generales y medicamentos de sedación en niños menores a 3 años o mujeres embarazadas. Esta advertencia se basa en la evidencia de la presencia de muerte celular, en particular apoptosis, en modelos animales a ser expuestos por horas a diferentes anestesias o sedantes. Sin embargo, la inducción de apoptosis no ha sido confirmada en humanos debido a la falta de métodos no invasivos que permitan la detección in vivo de estos efectos en el cerebro humano. Así, en colaboración con la doctora Chris Economidu y el Laboratorio de Ultrasonido Cuantitativo de la Universidad de Wisconsin, investigamos el potencial del ultrasonido cuantitativo por pulso eco para detectar cambios en la microestructura del tejido cerebral causados por la inducción de apoptosis por la exposición a anestesia en el cerebro del recién nacido. Para avanzar hacia este objetivo, realizamos un estudio preliminar de la sensibilidad del ultrasonido cuantitativo por pulso eco para detectar cambios microestructurales causados por muerte celular inducida por el anestésico sevoflurano en un modelo animal del cerebro neonatal. Los resultados que presentaré a continuación fueron parte de la tesis de licenciatura de Laura Castañeda, quien actualmente es estudiante de la maestría en física médica de la UNAM. Para este estudio, utilizamos datos de 20 macacos rhesus de 2 a 7 días de edad del Centro Nacional de Investigación en Primates de Wisconsin. 15 primates fueron expuestos al anestésico sevoflurano durante 5 horas, mientras que 5 fueron utilizados como controles. Los datos de ultrasonido fueron adquiridos en 2 sesiones. Una al inicio de la exposición a sevoflurano, donde no esperamos apoptosis, y otra 6 horas más adelante, donde esperamos apoptosis debido a la exposición prolongada a este agente. En este estudio nos centramos en estudiar los efectos del sevofluranos en el tálamo, que es un componente del diencéfalo implicado en la retransmisión de señales nerviosas a la corteza cerebral. Elegimos esta estructura porque es fácil de localizar en ultrasonido en modo B, tiene un patrón de moteado relativamente homogéneo y es altamente sensible a los efectos de apoptosis causados por el sevoflurano. En cada sesión adquirimos 15 imágenes en la vista coronal con un sistema Siemens S3000 utilizando un transductor de fase operado a 10 MHz y colocado a medio camino entre la fontanela frontal y posterior. A las 8 horas del inicio de la exposición a sevoflurano, extraímos muestras del tejido para corroborar la inducción de apoptosis a través de inmunohistoquímica. Para el análisis de ultrasonido cuantitativo por pulso eco, definimos regiones de estimación de parámetros en las porciones izquierda y derecha del tálamo, y en cada una de ellas se cuantificó el tamaño efectivo del dispersor. Los valores calculados se sometieron a criterios de aceptación basados en la presencia de razón señal a ruido espectral mayor a 15 decibeles para asegurar que no estuviéramos procesando ruido, y de similitud en la presencia de dispersión incoherente o difusa en ambos lados del tálamo. Es importante recalcar que la presencia de este tipo de dispersión es una suposición importante en la estimación del tamaño efectivo del dispersor. Por último, utilizando estos datos que pasaron en los criterios de aceptación, calculamos el cambio porcentual del tamaño efectivo del dispersor tras la exposición a anestesia. Estas gráficas son algunos de los resultados de este estudio preliminar. Solamente los datos de 6 animales pasaron los criterios de aceptación en el grupo expuesto a anestesia y de los 5 animales del grupo control. La gráfica de la izquierda muestra la correlación del cambio porcentual del tamaño efectivo del dispersor en función del grado de apoptosis en el tálamo, derivado a partir de inmunohistoquímica. Encontramos una fuerte correlación negativa entre el cambio del tamaño efectivo del dispersor y el grado de apoptosis. La figura de la derecha muestra un diagrama de cajas que agrupa los valores del cambio del tamaño efectivo del dispersor en el grupo control y el grupo expuesto a anestesia. Podemos ver que la magnitud del cambio del tamaño efectivo del dispersor es mayor en el grupo expuesto a sevoflurano que en el grupo control, en el cual el cambio del tamaño efectivo del dispersor está centrado en 0. En resumen, nuestros resultados sugieren que el tamaño efectivo del dispersor se podría utilizar para detectar de manera no invasiva la muerte celular causada por exposiciones prolongadas a anestesia en el cerebro del recién nacido. Actualmente estamos explorando nuevas técnicas de análisis de datos para reducir los efectos de la presencia de dispersión coherente que resultaron en un alto rechazo de los valores del tamaño efectivo del dispersor. Igualmente, estamos planeando las primeras aplicaciones en humanos. Para concluir, quisiera dejarles los siguientes mensajes. El ultrasonido cuantitativo tiene el potencial de proporcionar información valiosa sobre la estructura y la función del tejido, que aumenta y expande la información disponible para el diagnóstico, pronóstico y supervisión o monitoreo de la respuesta a un tratamiento dado. En particular, en obstetricia, el análisis de la propagación de ondas cortantes en el cervix tiene el potencial de proporcionar características cuantitativas para monitorear el proceso de remodelación cervical durante el embarazo. Y finalmente, en neonatología, el ultrasonido cuantitativo por pulso eco tiene el potencial de detectar cambios en la microestructura del tejido cerebral asociados a la inducción de apoptosis por la exposición prolongada a anestesia. Con eso concluyo, agradezco mucho su atención y con mucho gusto responderé sus preguntas.
Thank you, everyone. I would now like to introduce you to the moderator of our second webinar, Professor Roberto Lavarello. Roberto Lavarello is currently a professor at the Pontificia Universidad Católica de Peru in the Department of Engineering and the Director of Medical Imaging Laboratory in the MSc in Biomedical Engineering and a PhD in Engineering program. His research is primarily focused on the reconstruction and processing of images for the non-invasive assessment of pathological conditions. He is also an active member in the UFFC Society. Thank you, Roberto. Welcome to the webinar.
Thank you for the introduction, Lacey. That was a very good job pronouncing the university's name.
I appreciate it.
So, well, and thank you everybody for being here. This is a very, very important initiative for all of us in UFFC society. So let's take a look at the questions in the chat right now. And I think there's a couple of questions for Miguel. There's one from Ivan. He's asking if there was something special about the shape of the best performing apertures that made them stand out in terms of your performance metrics. He's asking or wondering if, for example, it was redundancy of sampling in the far field or something related that you could maybe try to elaborate a little bit more here.
Yeah, thank you, Ivan. Thank you for that question. I actually think is a great question, and unfortunately, I don't have an answer for it. You know, I've been wanting to do simulations to try to get the far field distribution of these apertures and see how precisely we focus the ultrasound intensity in it. But so far, I haven't had the time to do those measurements. But that's a constant question that I have in my mind is what makes those apertures better, and what I was trying to allude at the end of my talk is, can you optimize for one depth and then use it at a different depth, and can you still get those good results? Because it might be that you're only optimizing for a very particular thing. So that's a great question. I wish I had the answer at this point, but I don't.
No, sure, certainly. Thank you for your answer. Kuhn was asking also if is it possible to optimize the distribution of the sparse array such that it becomes sensitive for particular shapes. Like he's, for example, asking like lines for a blood vessel or spherical shape if you want to image tumors or something like that.
Yeah, and Kuhn, that's a great question, and I hadn't thought of anything like this, but it's super exciting. I think it could be done. I think the sparse random apertures, and you don't necessarily have to have them completely random. I think you can start creating patterns to try to identify certain features. So that's a very good and interesting question. But yeah,
May I add on this? If you use a full array, you create basically, or you try to create a dot in your illumination. But I could use it if you would use some smart excitation of your limited number of transducers, that you would create a spatial filter which would be sensitive for particular structures, surfaces, lines. But you never thought of this, trying to do something like that?
No, I haven't gotten to that point. And no, I have to be honest. I didn't, we've been working with row column arrays, and I've noticed that row column arrays, for example, are a lot better at distinguishing lines than they are of distinguishing dots or, spheres, just because of the way their array is constructed. So that's an excellent question, and that's a really cool idea. But no, I haven't started working on that. There's limited research that, limited time that I can use for research. So.
Thank you. Actually, there's a couple of more questions, I think. There's like 3 more questions. So let me see if I can get to them very quickly. So pertaining to your last point, Matthew is asking about other scenarios. Do you have any initial results how the trends you observe follow for in vivo or other situations?
No, I haven't had the chance to, here at Verisonics, we don't have the facilities to use animals or anything in that sense. So we're very limited to very simple phantoms. My next step was to actually do scanning on the CRS phantoms. But after that, I'll be happy to collaborate with anyone that that wants to give it a try.
I can give them a try. I'll be happy to. So let's see. There's another question here from Glauber, and he's asking, what is the spatial resolution of the system, and if you think there's any room for improvements on it?
I'm assuming that when Glauber asked about the resolution, he's talking about the ultrasound probe. If that's the case, the pitch of the probe is 300 microns. So this is a matrix probe that is like 1.5 by 1.5 centimeters. So we do the reconstruction at 1 wavelength, and since it's a big volume, I wish we could do it at half wavelength, but there's too many pixels, and the RAM can't handle it, especially if you're doing compounding of multiple apertures. So yeah.
Okay, thank you. And actually, I wanted to also ask you, like, and this may be a super silly question, because it may be, but do you get a feeling, you're working for the Latin American offices of Verisonics, if this 3D technology could be particularly useful for some, clinical applications that may be highly relevant to the Latin American region in particular? I mean, not that there has to be, but I don't know if there's something, that you're envisioning on that regard.
And I don't think we're targeting a region with this application. I do think that, it was for us imperative to be able to allow doing 3D imaging without the need of having, 4 systems. 4 systems, there's very few labs in the world that can afford to have, systems with 1,024 channels. So for us, it was imperative to, propose a solution. And, if this can help, Latin America start working on volume imaging, check, great. I'll be happy to, to see it happen. I'll be happy to help. I'll be happy, to participate.
Thank you. That's very, I was just wondering, because I mean, there's a, there's this whole thing about telemedicine happening in the Latin American region. There are groups that are collaborating with, groups in Peru, with groups in the US, for example, and they're very interested in scanning patients in places where there are no sonographers that would be, trained enough to collect the data, right? So they have these scanning protocols that allow them to collect data, it's volumetric data, and then there would be telemedicine or computer vision tools in order to locate, the things that, because I mean, basically you're obviating the need to have the sonographer. So I was just thinking, on the top of my head, like if maybe some of this technology could be amenable eventually, to try to enhance this type of examinations. But I think it's very, very interesting. Now, we have a couple of questions also for, let's see, we have a question for Ivan. We have more questions for you, Miguel, too, but I also wanted to ask questions to Ivan. So Hermes is asking, how does the scatter size change with the apoptosis? and what type of tissue damage is involved in the changes of the scattering pattern. And I actually wanted to, I actually had that question too, and I wanted to add on that if you compared it with, you know, histopathology images or something similar to elucidate this mechanism.
Thank you so much for that question. Can you hear me well?
Yes, we can.
Perfect. So that's an excellent question regarding explaining the scattering mechanism in the brain. So right now, our current hypothesis is that the main scattering source in the thalamus is the myelin of the axons of the neurons in the thalamus. And what happens when they go through apoptosis is that they go from being like elongated fibers to a recoil shape structure. I think that's what helps explain the reduction in the scatter size that we are seeing. Of course, there are other possible sources of scatterings like glial cells, oligodendrocytes that are also present in the thalamus. And but right now we don't have a direct one-to-one comparison with histopathology. That's something that we're doing in the future.
Thank you, Ivan. We have also a question from Sophie, who is asking: the brain is highly vascularized. How does the anesthesia effect on blood perfusion, pressure, and other parameters influence your quantitative ultrasound analysis?
That's another excellent question. We haven't looked at the temporal and spatial correlations of blood perfusion and possibly hypoxia caused by anesthesia. However, in our next step of the project, we are looking at the use of quantitative ultrasound in the context of perinatal asphyxia and stroke. So that would allow us to get deeper into that question. But we haven't looked at it directly right now. Yes.
Sure, thank you. Also, another question is related in my head to your the first application that you were talking about, the gynecological application, obstetrics application. So basically, you were exploring different types of parameters, right? Some of them use the longitudinal wave information, some of them use shear wave information, and a lot of people are trying to explore and observe, you know, correlations in between parameters derived from shear waves and longitudinal waves, non-complementary information and also redundant information in a sense. So from the results that you have gathered so far, maybe can you provide some insights on how this multi-wave quantitative ultrasound analysis, you know, can be useful? Absolutely.
So what I presented today was just a very small portion of what we've done with different quantitative ultrasound techniques. So what we're trying to do is to assess from different perspectives the remodeling of the collagen network of the extracellular matrix of the cervix. So what happens in the collagen network of the cervix is that when pregnancy starts, and in non-pregnant women, as I show in the second harmonic generation images, the collagen is forming bands around the cervical canal. So it's a highly anisotropic, well-structured tissue. And as pregnancy progresses and the cervix softens, this occurs because the collagen fibers become disorganized and more spaced by water and the other molecules that compose the extracellular matrix. So that helps explain the softening that we detect with the shear wave elasticity method. We have also looked at using the pulse echo quantitative ultrasound techniques, like looking at effective scatter size, looking at speckle statistics, looking at the attenuation coefficient, and all of them that point in the direction that disarrangement of the collagen fibers occurs at the same pace at which the cervix is softened, as indicated by the shear wave elasticity technique. So for example, using speckle statistics, we observed that the Nakagami parameter, which is related to the density and the randomness of the collagen network in the tissue, indicates a more diffuse scattering process, which agrees with the hypothesis that the collagen disorganizes. We have also observed a decrease in the effective scatter size in the collagen, and all those features indicate that the collagen breaks down, and that contributes to cervical softening, as we measure with shear wave elasticity imaging. So we're constructing the whole story, as you say, from having not only redundant, but information at different scales, right?
Correct, correct, which is fascinating, I think, from that particular field. Thank you, Ivan. And Hermes tells me that we have maybe time for one more question. And I have one from you actually, Ivan, to Miguel. So we can maybe wrap it up with that question, Miguel. A very short one. Any thoughts about using space random aperture for further sparsity bubble detection? Questions or thoughts about that for ULM? Any questions or thoughts?
Honestly, I think that would be a really exciting, experiment. Yeah. I think it should be able, to provide a good signal, and you can always start with one random aperture and then two, and this way you can also control a little bit, the intensity of the ultrasound so that you don't, burst the bubbles. So I think, that would be cool to try. Again, I'm open to a bunch of applications.
I'll send you a private message. Thank you, Miguel.
No, honestly, it's I'm excited that we developed this tool or this technique, but it will be really cool now to, and I don't want this to sound, like I'm trying to sell the system or the technique, but those examples are, for example, in our Vantage release, all the scripts to create those images that I showed, or the acquisitions that I showed, are actually in our releases. So, you guys have access to them. I know, Ivan, you guys have used our system. So yeah, private message me and we can talk about this.
Excellent. And Hermes, I think you had an announcement to make, and thank you to everybody for the questions. I mean, this was a lot of fun.
That was very nice. I think this initiative is exactly about that, right? So communicating, sharing this experience, potential collaborations, this is great. Before you all leave, I just want to ask you to answer some questions. Lacey will post these questions. It's a feedback for us how this format is, how do you like it? And then we can improve the webinar if needed. Thank you so much, everyone.
Yeah, as you can see, I've launched the polls. The first question is, do you think subtitles are helpful for webinars? The second question is, what would your preferred presentation format be? Is it pre-recorded with subtitles, or is it a live presentation? And then question 3 is, what types of talks would you like to see next? Academic, industry, or educational? We'll give everybody about a minute or two to answer those. We appreciate it. Great. I believe everybody has voted. We'll stop the poll and I will share the results now. Thank you everyone for your participation with our polls, and thank you so much for joining us for the second webinar in the UFFCS America Latina and Foco series from the IEEE-UFFCS Latin America Outreach Initiative. Please stay tuned for our further webinars in the future, and reach out to any of the following volunteers if you have any questions or ways to get involved. We really appreciate your participation. Thank you, everyone.
Thank you so much.
Thank you, Ivan and Miguel.
Bye, everyone.
And Roberto. Have a great day.
Thank you, everybody. Bye.
Bye-bye.